Ever wondered how machine learning algorithms make predictions? Well, one of the ways is through a method called naive Bayes. Machine learning, in essence, is a technique that allows computers to learn from data, much like how we humans learn from experiences. It's used to make predictions and decisions without being explicitly programmed to do so. Now, within the realm of machine learning, there exists a simple yet powerful algorithm for predictive modeling, known as the naive Bayes method. It's based on Bayes' theorem, a fundamental concept in probability theory and statistics. The naive part of it comes from an assumption that the method makes, which we'll delve into later. This algorithm is widely used in various fields, from email spam detection to sentiment analysis and even in medical diagnosis. Intrigued? Let's dive deeper into understanding this fascinating method. To understand naive Bayes, we need to grasp a few fundamental concepts. Let's start with conditional probability. Think of it as a way to measure the likelihood of an event given that another event has occurred. It's the backbone of naive Bayes, influencing how it calculates predictions. Next, let's delve into the Bayes theorem, named after its creator, the Reverend Thomas Bayes. This theorem calculates the probability of an event based on prior knowledge of conditions that might be related to the event. It's the secret sauce that adds flavor to our naive Bayes algorithm. Finally, we come to the algorithm itself. In machine learning, naive Bayes uses these concepts to predict the category of a sample. It does this by taking into account the features of the sample and using our old friends, conditional probability, and the Bayes theorem to make its predictions. With these basics, we're ready to explore how naive Bayes works in machine learning. Now let's see how naive Bayes functions in the realm of machine learning. Imagine you're a detective, and your task is to predict the outcome of an event based on available clues. This is essentially what the naive Bayes algorithm does. It uses probability theory and Bayes' theorem to predict the class of an object based on its features. The first step in using naive Bayes is training the model. This involves feeding the algorithm with data or clues about past events. These could be anything from the color of an object, the time of day, or even the weather conditions. Each of these clues is considered a feature, and the combination of all features forms an event. Once the model is trained, it's time to calculate probabilities. The algorithm uses the clues and applies Bayes' theorem to calculate the probability of each outcome. This is where the Bayes in naive Bayes comes from. Now let's say we have a new event and we want to predict the outcome. The algorithm will calculate the probability of each class or outcome based on the features of the new event. It will then assign the event to the class with the highest probability. And just like that, you've made a prediction. This is the essence of naive Bayes in action. It's a simple yet powerful tool for making predictions based on prior knowledge. And that's how naive Bayes works. But why do we call it naive? You might be wondering why this method is called naive Bayes. The naivety lies in its assumption that all features in a dataset are independent of each other. This is often not the case in real-world data, but this assumption simplifies the calculations tremendously. It allows us to treat each feature individually, calculate its probability, and then multiply these probabilities together. This ease of computation is why we keep it naive. Despite its simplicity, naive Bayes is a powerful tool in machine learning. So, what have we learnt about naive Bayes in machine learning? Well, we've delved into the heart of naive Bayes, unearthing its foundation on conditional probability and the Bayes theorem. This powerful algorithm is a go-to tool in the machine learning toolbox, often used to make predictions. We've also explored its naivety. Despite its name, there's nothing foolish about it. Naive Bayes assumes independence among features, which, while not always entirely accurate, greatly simplifies computation. This simplification is what makes it so practical and efficient, enabling it to handle large data sets with ease. We've seen it in action and appreciated the role it plays in the real world. It's more than just an algorithm. It's a silent operator, working behind the scenes in areas we often take for granted. So next time you wonder how your email filters spam or your search engine predicts your queries, remember, it could be naive Bayes at work.